In Notes B, we're going to discuss some periodic trends. We're not only going to talk about what the trends are, we're also going to get into what causes some of these trends to exist. This video will go over 6 specific trends on the periodic table: valence electrons, atomic radii, ionic radii, electronegativity, ionization energy, and a new one, melting points. You may have wondered where the name periodic table came from. The term periodic actually means repeating patterns, happening periodically, much like periodic motion in physics. So the term periodic table just means this table presents multiple patterns. The first trend that we will look at is the number of valence electrons for each atom. So first we should talk about what a valence electron actually is. At this point you should know that the outermost electrons are your valence electrons. Well, where did that term come from? There's actually a Latin word val that means to be strong. They were named this because most valence electrons are the basis behind chemical reactions. For example, alkali metals are extremely violently reactive with water. Since they only have one valence electron, it is very easy for them to have this very explosive volatile reaction. Whereas aluminum, on the other hand, having 3 valence electrons, wouldn't react with water. You would just have aluminum floating around in a bucket of water. But if you throw sodium in water, you get this violent reaction, or this explosive exothermic reaction. And that's because of the number of valence electrons. There's kind of an irony here if you think about it, because the valence electrons would be the ones furthest from the nucleus. They would have the weakest attraction to the atom's own nucleus, so you wouldn't really think of that as really being strong. But where the term originally came from, it's talking about the strength in driving a chemical reaction. So it's kind of in control. One last thing that you should know about electrons is there is a special term for the non-valence electrons, and we call them core electrons. So say an atom comes with 100 electrons, only the outermost shell, which can have up to 8 electrons, would be your valence shell. All the other shells inside, all of the other energy levels, contain core electrons. The inner shells tend to be completely full shells, and so core electrons are going to be relatively stable, which is why your valence electrons are the reason for your chemical reactions. You can identify valence electrons from an atom's electron configuration. Here we have chlorine. When you look at the electron configuration, the large number in front of the orbital tells you the energy level. So in 1s2, that tells me I have 2 electrons in an S-shaped orbital at the first energy level. In the second energy level, I have 2 electrons in an S-shape and 6 electrons in a P-shapes. Remember, P came in sets of 3. And then in my third energy level, I have 2 electrons in an S-shape and 5 electrons in the P-shapes. The highest principal quantum number there would be 3. So that means the third energy level must be my valence shell. This is going to drive a chemical reaction because we want full energy levels, full sublevels in order to reach stability. That is what drives a chemical reaction. So by seeing that we have 7 total valence electrons, it tells me I want to gain 1 electron in order to get a complete octet. So chlorine will be very reactive with anything that will help it get that 1 extra electron. Let's look at a different element like cadmium. Here we have its electron configuration. What would be the valence shell here? You've got to scan through and try to find the highest number, the highest principal quantum number, large number before the letters. In this case, it's going to be 5. 5s2 is my valence shell, which means that in this case, the atom wants to actually lose. It is easier to lose 2 electrons as opposed to trying to gain 6 more. So this means that cadmium would be more reactive with something that would make it lose 2 electrons, whereas the chlorine would be very reactive with something that would help it gain 1 electron. The electron configuration, or the number of valence electrons, can actually tell you a lot about an atom's reactivity. Looking at the periodic table can actually tell you exactly how many valence electrons an atom has, as long as we're not dealing with the transition metals, which can have several exceptions. So if you look at only the tall groups, the first group, the alkali metals, would have only one valence electrons. Then next group over, alkali earth metals, would have 2 valence electrons. The periodic table that we have hanging on the wall actually numbers the transition metals 3 through 12 and then picks up at 13, which I always ignore, and I always just call this group 3 through 8, but it is actually numbered 13 through 18. You're still going to go with 3 valence electrons for the first group, all the way out to our noble gases would have 8 valence electrons. Next, we're going to go over the 3 things that drive our periodic trends. Before we go over the trends themselves, we're going to talk about why these trends happen. It's actually 3 specific explanations that apply to all the trends. The first factor is how many protons are in the nucleus. Protons are positive, and a lot of our trends are going to talk about where the electrons are or how easy they are to remove. So opposites attract. How attractive is the positives that are in the nucleus? How good is that at pulling the electron in? The second thing that we're going to talk about is the actual distance. If I have a nucleus and an electron, how far apart are they? The actual distance they are apart. And then the last thing that we're going to talk about is once they have established that they're far apart, what if there's something else in the way, some other electrons on inner energy levels? So we actually call that the shielding effect. This is kind of the blocking of the attraction. The positive and negative are attracted, but these negatives are pushing the electrons away. This demonstrates our first factor. If there are more protons in the nucleus, they will be able to pull harder on the electrons. This will lead to things like smaller atoms, also higher ionization energies and greater electronegativities. As the electrons are more attached to that proton group, they're going to be harder to remove or pull away from that atom. This represents our second factor, the actual distance between the positive nucleus and the negative electron. We can actually use physics to enhance this explanation. This is a formula for something called Coulomb's law. In this formula, K is a constant and the Q would be the charges of the 2 separate particles. But you can see that it's divided by r squared. R, radius, would represent our distance between the protons and the electrons. So as you increase the distance, you actually decrease the force felt, that force of attraction felt by the electron, which affects how easy it is for that electron to be stolen. So you're going to see the distance actually affecting trends like ionization energies and electronegativities. The third factor is the shielding effect. The shielding effect refers to a shield that is actually formed by the inner electrons. So the more core electrons or inside shells that are in an atom, the more repulsive forces the electrons will feel against each other. So my valence electron is being pushed away by the inside electrons. More core electrons will mean more repulsive force. So this means the atom is going to have an easier and easier time giving up that outside electron, again affecting trends like ionization energy and electronegativity, as the shielding caused by those core electrons affects the amount of repulsion. Really big distinction here from the last factor. The second factor focused on the amount of attractive forces, the distance increasing or decreasing that force, whereas this third factor focuses on the amount of repulsive forces caused by the shield, the core electrons. IB needs you to be very specific about both of those forces being a factor. IB integrates some physics into this, so we want to be able to describe both attractive forces and repulsive forces. Yes, they go in the same direction. As I have more core electrons, I'm going to be further away, so the force of attraction would go down, and more core electrons, so the force of repulsion would go up. So both of those things are making the electron easier to steal. but there are 2 reasons why it is easier to steal. Now that we've gone over the 3 factors, we're going to apply that to some specific trends. Our first trend will be the atomic radii. So a quick note on why we use the radius to describe the distance from the nucleus. Can you imagine trying to find the distance from one side of an atom to another side of an atom? How would you know exactly where to put the ruler, for lack of a better term? How do I know where that outside actually is? How do I know where those shells exist? Those shells move as they fill. It's very hard to actually measure. So instead, we've defined the distance between a bond and just cut that in half, calling it the atomic radius. It is a minor detail to allow us to get some more reliable numbers, but because of the way this is done, you will note that there is no radius given for the noble gases since they don't bond. As you go down a group on the periodic table, for example, in the alkali metals from hydrogen all the way down to francium, the radius will get larger. There are 2 reasons for this. As you go down, you're increasing the principal quantum number. Hydrogen only has a 1s orbital, whereas lithium has 1s and 2s. And sodium also has a 3s, all the way down to francium having a 7s. So you have more energy levels. That literally means that they are further from the nucleus. In addition to this, now there are more core electrons, so you also have the shielding effect. So 2 factors, the actual literal distance and the shielding effect. As you get more and more core electrons, it's going to push those extra energy levels even further and further than they would be without that shielding. So make sure you mention both factors. As you move across a period from left to right, for example, let's go across row 4. So from potassium all the way out to krypton, you'd go across your 4s, your 3d, and your 4p energy levels. As you do that, the atomic number is increasing from 19 all the way up to 36. That's more and more protons being added to the nucleus of the atom. More protons will pull harder. So as you add more protons, those electrons are going to be more strongly pulled towards the nucleus. This, in effect, will shrink the atom. Next, we're going to talk about size as the atom changes into an ion. So there's actually quite a few trends on this slide. The first thing that I want to point out is that if I have a cation, that will always come from a metal, and then if I have an anion, that will always come from a nonmetal. And that has to do with where the metals and nonmetals are on the periodic table. Metals are on the left, typically having 1, 2, or maybe 3 valence electrons, so for them it's easier to lose an electron, whereas anions are on the right-hand side of the periodic table, the nonmetals typically having 7, 6, maybe 5 valence electrons, so for them it would be better to gain electrons. So if they gain electrons, they become negative anions, and if they lose electrons, they become positive cations. Now let's look at what happens when you lose an electron. In sodium's case, the 3s orbital would be its valence electron, and so if it loses that electron, it would then become smaller. What's going to happen is the entire 3s orbital would then disappear, making the second energy level now the valence shell. So where I had a 3s orbital with 1 electron in it, if I remove that electron, the atom is then smaller. There's less overall repulsion, and an entire energy level is now gone. Now I only have 2 energy levels instead of 3, so the distance is smaller. Finally, let's look at what happens when you gain an electron. In chlorine's case, the valence shell would be, again, the 3rd energy level, but this time there are 7 electrons in it, 3s2 and 5p5. So in order to follow the octet rule, chlorine would actually gain 1 electron right here in the p orbital, because we would want this complete 3p6 orbital. As it gains an extra electron, it still has the same exact number of protons. Its atomic number didn't change. An ion still has the same atomic number as the atom. So what this means is that there's more repulsion, but still the exact same attraction and the exact same distance. So that extra repulsion pushing is going to make the atom spread out a bit larger. I do have to comment that I don't necessarily think that this picture is a good scale. When you go from 3 energy levels to 2, you do have a significant shrinkage. But when you go to just add in one more electron, you're only going to get a minor increase. All you really need to know, though, is when it gets smaller as opposed to when it gets bigger. I just wanted you to know that this doesn't really seem like it is to scale. Now that we've gone over how an ionic radius changes compared to its own atom's radius, I do want to comment that the ionic radii is based on atomic radii. So if the atom is increasing in size as you go down the group, both cations and anions would follow that pattern as well. When we say they're bigger or smaller compared to their atom, I am just talking about like a sodium positive ion compared to the sodium neutral atom. But still, a sodium positive ion would be smaller than a potassium positive ion because the potassium atom was larger than the sodium atom in the first place. The same is true as you go across the period. If the atom has more protons, the ion would also have more protons. So for example, oxygen is smaller than nitrogen because oxygen has more protons than nitrogen. The oxygen ion would also be smaller than the nitrogen ion. So basically comparing ion to ion works exactly the same way as comparing atom to atom. But if you compare an ion to its atom, then that's different. Cations are always smaller than their original atom, and anions are always larger than their original atom. The next trend we're going to discuss is called ionization energy. And to be very specific, we are going to look at the first ionization energy of every atom. Remember that IB has a very specific definition for first ionization energy, as opposed to second ionization energy or subsequent ionization energies. Remember that the atom first has to be a gas, and it is the energy only to remove exactly one electron from the valence shell. So we take an individual atom, we give it a +1 charge, only removing one electron, but it has to be a gas already. So this should be a very familiar graph coming out of chapter 2. This is different than the graph in chapter 2 that showed subsequent energies. Remember, we are comparing atoms to each other, so we're comparing the first ionization energy of different atoms. This graph does show evidence of sublevels. Let's look at the first ionization energy of the first few atoms. Here's hydrogen versus helium. Both of these atoms only have the 1s orbital, but for helium, that orbital is full because it has 2 electrons, whereas hydrogen only has 1. If you look at lithium going up to neon, neon has a completely full second energy level, 2s2, 2p6, whereas lithium only has 1 electron in the 2s orbital, so it's way down lower. If you compare beryllium to boron, beryllium is higher because it has the s orbital full, whereas boron is starting to fill the p orbital. So removing 1 electron from boron would require less energy because it would be more stable to have the full s orbital, whereas beryllium, if you're removing it, you're breaking up that full s orbital. So you see these dips and valleys as you have your either perfectly half full or completely full orbitals. There's a lot more detail on this in the video for Notes D Part 1, Ionization Energies. Granted, there is evidence for sublevels. When we look at the trend overall within a group, you do see a general increase as you go from the left side of the periodic table to the right side of the periodic table. You can also compare the trends as you go from row to row. So that's what we're going to focus on in the next couple of slides. As you go down a group, for example, from hydrogen to francium in the alkali metals, the ionization energy is going to decrease, which basically means it is easier and easier to steal the electron. That's because as you go further and further away, the protons are further and further apart from the electrons. So the distance, or the R value in Coulomb's law, is going to increase, which is basically going to decrease the force of attraction. Additionally, you are going to have more shielding because you will have more and more core electrons. So as you have more and more shielding, you're going to get more and more force of repulsion. So you get increased repulsion, but decreased attraction. Both of these things are going to make it easier to steal the electron. But I really need you to differentiate the force of attraction versus the force of repulsion. Those are two separate factors, distance and shielding. As you go across a period from left to right, you're going to have more and more protons as the atomic number increases. If you have more protons, you have more pull on the electrons. That increased force of attraction is going to make it harder to remove the electrons. The next trend we're going to talk about is electronegativity. Electronegativity is very similar to ionization energy. In fact, the trends are actually going to match up. The difference is with electronegativity, we're talking about a covalent bond, whereas in ionization energy, that would apply to forming ions, more like an ionic bond. With electronegativity, I'm looking at how likely the atom is to be the greedy atom and attract those electrons, basically be less likely to give them to the other atom more often. Keep in mind they're shared overall, and the electronegativity is going to show how strongly the atom will attract those shared electrons. As you go down a group, you're going to have a larger size and more shielding, so that atom is going to be less invested in pulling the electrons towards it, hence the lower electronegativity as you go down a group. As you go across a period, you're going to have more protons, more pull. So you're going to get that attraction, so the atom would be more invested in keeping the electron close to it in a shared bond. There is one small catch. Noble gases don't bond, so how can we tell whether they are good at sharing in a bond? So we are going to stop our trend for electronegativity at the halogens instead. Finally, we're going to discuss the most complex trend, the melting point. Melting point trend actually is different depending on what type of atom you have. So we're going to start with looking at only the metals. As you go across a row with metals, you're going to see an increase in the melting point. So as you go across the second row of the periodic table, from lithium to beryllium to boron, you see an increase. As you go across the third row, from sodium to magnesium to aluminum, again an increase. And comparing potassium to calcium, again, increase as you go from left to right across a period, but only for metals. Next, we'll look at the metalloids. We have carbon and silicon shown here. The metalloids are always the peak. So you see carbon is the metalloid at the top of the graph for group 2, and silicon is at the top of the graph for group 3, or row 3. And last, we'll look at nonmetals. The trend for nonmetals is not just a decrease, but it actually says it drops. Notice the gigantic drop-off between carbon and nitrogen, or similarly between silicon and phosphorus. When you go from metalloid to nonmetal, there is a deep dive in melting point. So we are way down lower temperatures, dropping the melting point, but as you go from the metalloid to the next nonmetal. That being said, if you compare within the nonmetals, there is a decrease. There is a slight dip as you go from hydrogen to helium, from nitrogen to neon, or from phosphorus to argon. There is a general decrease. However, since the drop from the metalloid down is so drastic, that decrease isn't always the most noticeable. In order to understand why the melting point trend is so different for the different types of atoms, we have to think about what melting point really represents. An atom would go through the transition from a solid to a liquid when there's enough energy to interrupt the intermolecular attractions between the atoms. So the melting point is going to depend on two basic things: the structure of the element, how it's held together, and how strong those attractive forces are between two atoms of the same element, So the element itself, the atom itself, and then what attractive forces go between two atoms. Let's apply this first to the metals using period 3 as an example. Sodium, magnesium, and aluminum are all metals. They're on the left of the stair-step line. I know the structure of them will give me 1, 2, or 3 valence electrons based on their location on the periodic table. So let's think about what type of intermolecular attractions would be between two sodium atoms, or between two magnesium atoms, or between two aluminum atoms. What would hold one sodium atom to another would have to be metallic bonding. So as I have metallic bonding, I have something called the electron-C model, which basically means I have free-flowing electrons. The more valence electrons I have, the more electrons would participate in that electron-C model. So basically, if I have more valence electrons, I have a stronger metallic bond. So aluminum would take the most energy to melt, whereas sodium, with only 1 electron in the C per atom, would have a much weaker metallic bond and would take much less energy to melt. The peak for period 3 would be silicon. Silicon is the metalloid in the middle of the period, the one that touches the stair-step line. The reason that the silicon takes the most energy to melt is that it has a very special structure. They call it a macromolecular or large molecule covalent shared structure. You may also hear this called a network bond. We're going to talk a lot more about this in chapter 4. The idea is that there's just huge networks of hundreds and hundreds of atoms that connect together in a very specific crystal type of structure, very uniform, repetitive structure, different types of blocks that come together. So this basically is a super strong way to connect. Very strong bonds would mean a very high melting point. Now let's look at some nonmetals. As we go down period 3, we're going to come across phosphorus, sulfur, and chlorine. As nonmetals, they're going to form simple bonds. They aren't going to form large groups, not macromolecular, just simple bonding, but they will bond with themselves, which means we're not even going to have polar bonds. We are just simply going to have usually London dispersion forces as our intermolecular force. There is a new term on this slide I really want to highlight: van der Waals forces. Basically, van der Waals forces refer to any type of intermolecular force. This will come up again as we discuss bonding in chapter 4. The intermolecular force or van der Waals force that we're referring to with this particular trend in the melting point of nonmetals is your London dispersion forces. It's basically very weak, minute forces that exist for fractions of milliseconds as the electrons just rotate around within the atoms. So that's going to create very small partial positive and partial negative attractions. A larger atom would have more and more space for these electrons to kind of gather in partial positive and partial negative pockets. So the larger the atom, the greater the London dispersion forces or the intermolecular forces would be. So phosphorus, being the largest atom of the group, would have the largest melting point, and then as you go down to chlorine, you would have the smaller melting point. Since chlorine has more protons, it would be a smaller atom. It would hold them more closely. Less delocalization leads to the weaker bond and a weaker melting point. Less energy needed to break up the attraction between the particles. The very bottom of any period would be the noble gas. So for period 3, that would be argon. Argon has the lowest melting point out of any atom in period 3, starting with sodium and going all the way through to argon. Argon is at the very bottom. Argon does not even have a covalent bond. Noble gases do not bond. So at least if you had 2 chlorine atoms, the electrons could be delocalized moving between the 2 chlorine atoms. You're going to get more partial positive and partial negative pieces. With argon, it is literally just the electrons rotating within the argon atom. That's going to create less positives and negatives as the electrons move because they have less space to move. So the weakest LDF forces belong to the noble gases, meaning they would take the least amount of energy to melt. Now let's look at what happens when you go down a group. As you might expect, the trend will be different depending on whether you're going down a group of metals versus the nonmetals. So let's first just look at a group of metals. This is our alkali metals, just looking at going from lithium down to cesium. We can see the highest melting point is at lithium, where the atom is small, and then we have cesium having our lowest melting point, and the atomic radius increasing as you go down. Cesium would be the largest atom. Keep in mind that for metals, what holds them together are metallic bonds. The metallic bond strength actually comes from the electron C. So if an atom is larger, they're going to be more separated from that electron C, therefore decreasing the metallic bond. So the larger the atom, the less energy required to interrupt that attraction. The melting point would therefore decrease. If you look at a group of nonmetals, you're going to actually see an increase as you go down the group. Here we start at fluorine of our halogens with a melting point of only 53 Kelvin and go all the way up to almost 400 Kelvin with the iodine. So we're seeing an increase, a big increase in melting point as you go down the group. And that's because as you go down the group, the atoms get bigger. Where this goes against the strength for the metallic bond, it actually helps the strength for the nonmetals. And that's because what's attracting them to each other are simply van der Waals forces. In order for van der Waals forces to get stronger, you just need delocalization, places for the electrons to move and gather to get these partial negative and partial positive areas. The more delocalization, the stronger the bond. So with iodine being a much larger molecule, the electrons can move around more and you're going to get those stronger attractions, meaning it would take way more energy to interrupt those intermolecular attractions compared to the smaller atom, where fluorine has the electrons that can only move so far. Since it's a much smaller atom, you're going to get much less of this gathering of positives and negatives as the electron moves around. So that would be a much easier bond to interrupt because you don't have as much of polarity, for lack of a better term, attraction between the partial positives and partial negatives created from the LDF forces. So basically, larger nonmetals will have much higher melting points as opposed to larger metals, which would have much smaller melting points.